Okay. Hi, everyone. Welcome back to the second lecture, which marks the start of Geoffrey's course. So I wanted to give a warm welcome to Professor Geoffrey Lovelace, who's come here from California State University, Fullerton. So Geoffrey has been a numerical relativist for many years. He's one of the core developers of the spectral Einstein code, which I've already described as one of the leading codes around in literature, which has been responsible for various follow-ups of various gravitational waves events that we have seen so far. And Geoffrey especially has been known for attacking some of the most technically challenging simulations, especially those of nearly extremely spinning black hole binary systems and so on. And these days, he's spending a lot of his time developing the next generation of numerical relativity infrastructure through an open source toolkit called Spectre, which he's going to tell us a lot about this whole week. So Geoffrey, do you want to maybe start?
Sure. Thanks for the invitation. I'm really happy to be here. I should say, when I was a PhD student, first learning numerical relativity, I learned it from Harold. Harold was a postdoc when I was a grad student. And my first projects, Harold, I'll supervise them. So anything that goes well in my lectures and tutorials, I would give Harold a good share of the credit. But anything that I screw up, that's me. That's not Harold. Okay. Now I'm going to go to the board and do some math later on in the week. But I felt like the math was enough that I wanted to motivate it first. So I'm going to show some slides and some movies and pictures to say, why am I going to ask you to go through the stuff we're going to go through the rest of the course? And what is the big deal? Why isn't numerical relativity just solved? Why do we need a next generation of numerical relativity? And because the answer has to do with next generation gravitational wave detectors, I'm actually going to stray away from numerical relativity a little bit to just make sure we're all on the same page about gravitational wave observations too. So to start out, my slide clicker's not working. Oh, let's see. Now, there we go. So here's what I want to do in the course. There's sort of two parts, the lectures and the tutorials. Today is going to be a little different than the rest of the week. Most of the week, I'm going to be showing you how to work through the mathematics of what the discontinuous Galerkin approach to doing numerical solutions of partial differential equations, but in particular equations that are at least sort of suggestive of the kind we want to do to solve binary black holes. And that's what we'll be doing most of the time. Today, I'm going to say something about why. Why do we need next generation numerical relativity? And then I'll say a little bit to first introduction of two different techniques. And these are going to be the focus of the course. Two different techniques that are the next generation part of next generation numerical relativity. The first technique is discontinuous Galerkin. And that's what we'll talk about in the lectures. The second technique is task-based parallelism. And that's what we'll focus on mostly in the tutorials. If there's time today, I might introduce it a little bit. In the tutorials, the idea is I didn't make problem sets. I'll be here in the tutorials and I'll have my computer up on the screen. And the idea is I want you to get in groups and code along with me in the tutorials. And I'll show you, oh, something's happening back here. Okay. So I'll show you how to, with no prior experience, I'll give you a crash course on C++. Harold alluded to this. When you care about performance, Python isn't fast enough. You need C++. So, and Spectre, the code I'm going to show you as an example of task-based parallelism, even if you've seen C++, you probably haven't seen it like this. So I'll take you through a crash course of some of the things that we do. And after that, the rest of the tutorials are going to focus on building a simple example that demonstrates task-based parallelism. It's kind of hard to get your mind around how different it is unless you actually try to do it. And along the way, you'll know enough C++ and Spectre that if you got interested in working on the Spectre code, you would have a foundation to do that. So that's sort of the plan. I wanted to say please, please don't be shy to stop and ask if you have questions. If I say something you don't hear or can't understand or you're not sure, chances are if you have a question, someone else is wondering the same thing. I really don't think there's such a thing as a dumb question. Please don't worry about it. You can ask really hard ones too, and then maybe I won't know, but you can ask anything. And when I write on the board, Harold said his handwriting is bad. I thought it looked good compared to mine, so I'll do my best, but please let me know if I need to rewrite something. Okay, so with that out of the way, let me start out by talking about numerical relativity and gravitational wave observations, just to set the stage. And this is going to build up to why are we building a new numerical relativity code that uses discontinuous Galerkin and task-based parallelism. Okay, so to start out, here's a movie from the SXS collaboration. This is using some, I don't remember who did the final render, but Harold made a lot of the techniques that let you make movies like this. So this is showing two black holes orbiting each other. This part here is showing the scalar curvature. It's meant to be sort of like an embedding diagram, and the color is the rate of flow of time. It's the lapse, if you remember back to the lecture last week from Thomas Baumgart. And now as the black holes orbit, they start going faster and faster, and as they do, down here, this blue color is showing the stretching and squeezing of space caused by the gravitational wave. The amplitude and frequency go up as they're about to merge, and then it'll pause while they merge and then settle back down. Now, this might be familiar, but I wanted to start here because at this moment, right here, this is ultimately why we have to do numerical relativity. The equations are too nonlinear. No one knows how to solve the equations here right at that moment without numerical relativity. Okay. Now, out here, it's going to zoom out and show the gravitational waves. They're traveling off at the speed of light, so this is definitely slow motion, and they're going off toward infinity. All right, so this is the basic process that is the goal for one of the goals of numerical relativity. There's also matter, but empty space is hard enough for me, so I'm going to stick with vacuum for the most part. You heard last week about some of the extra complexities and richness and cool stuff when there's matter involved in the simulations. Okay, so that's what happens when two black holes merge and emit gravitational waves. But what do those gravitational waves really do? Even though this is really going to focus on numerical relativity, I want to say something about the experiment that's the motivation for all this. So what really happens when a gravitational wave comes by? So imagine a gravitational wave is coming right out of the screen towards you, and you've built a circle of little test particles. Maybe the radius of this is the radius of a gravitational wave detector, like LIGO, 4 kilometers, say. All right, and what I'm showing is what the gravitational wave would do. Maybe you've seen something like this before, but just to get our bearings, this is showing a stretching and squeezing the way a gravitational wave coming right through the screen would do. And what I'm showing here is a change of 1 in 10. So this would be a strain or a fractional stretching and squeezing of 10%. So the length is, if it's 4 kilometers, the length is changing by 10% of that, or 400 meters. All right, so just to set the scale. Now this is greatly exaggerated from what the actual gravitational waves do. The loudest waves passing through Earth that we know of create a change not of 10 to the minus 1 or 10%, but a fractional stretching and squeezing of 10 to the minus 21, 1 part in 10 to the 21, this ridiculously small thing. So the first thing I wanted to do with this is just get the idea of the scale, and also ask you a couple of quick little questions to show you what we're going to do with all these ABCD cards. Did anybody come in and not get one of these yet? Anyone need one? Okay, great. I'll tell you what to do with them. So I'm going to ask you a question, and I'm going to have just a few of these throughout the lecture. Now, I don't want you to do anything until I explain how these cards work. The idea is we'll look at the questions and think about them for a bit, and then after a little while, I'll say prepare your votes. When that happens, pick the letter you want to vote on the card, and then fold it. So if you wanted to vote, I haven't even looked at it. I don't know what the right answer is without looking, but if you wanted to vote D, you would fold it like this and keep it down. You would fold it, but keep it down. And then when I say hold up your votes, you'll hold them like this. You'll look silly, but everybody will be doing it. And the reason to hold them here is no one else can see your vote, so it gives you a bit of anonymity. It's totally fine to get these wrong. There's no grades in this course anyway. And then, depending on how it goes, if you get it right, I'll ask you all to tell me what the right answer is. If there's some disagreement, I'll ask you to talk to someone near you and try to convince each other what's right. Now, this question might be a little elementary, but just to get used to the cards and things and just to get you thinking, let's just start with this here. So think about it for a bit, and then we'll vote. Where's the E? Good question. Where's the E? Right here on the back. Okay. All right. Would anyone like to think a little longer before we vote? That's always okay. If not, prepare your vote. So don't hold them up yet, but fold your cards the way you want to vote. And now hold up your votes. Let's see. Okay. Hold them up under your. Okay. Go ahead and put your votes down. There was actually kind of a spectrum of opinions here. So what I'd like you to do is turn to someone next to you, introduce yourselves if you don't happen to know each other, and try in the next 30 seconds or so pretty quick, try to convince them why you're right. And then we'll vote again in just a little bit. Okay, let's come back together and see how persuasive you were. Did you convince each other? Prepare your votes one more time and hold up your votes one more time. Okay. Great, put your votes down. There was a very nice shift towards the correct answer, but it wasn't quite unanimous. So I'll just say a little bit about this. So this might not be a number that you carry around in your head. The size of a proton, does anybody remember to the nearest power of 10 how many meters a proton is? Yeah, 10 minus 15 meters. Now, if you start out with something of order 10 to the 3 meters, and the fractional change of that 10 to the 3 meters is 10 to the minus 21, 10 to the minus 21 times 10 to the 3 is going to be 10 to the minus 18. So the correct answer to this question is, in fact, what? It's E, exactly right, exactly right. It's this incredibly small thing, the most precise kind of length measurement anyone's ever had to do. And I wanted to start with this because the fact that this is so small, you can work out with some scaling argument like this, but this fact is why we need better numerical relativity when it comes right down to it. It's because the measurement is so difficult that we need the theory to help us interpret the observations. Okay, now, I'll just skip through this slide, but you have to go down a lot of powers of 10 to get down to the 10 to the minus 18 meters. Okay, so how does LIGO do that? Well, this is Einstein's paper predicting the existence of gravitational waves. And I guess I could ask Harold to translate. I don't speak German, but I've got a translation on here. And Einstein said A, which had to do with the strength of gravitational waves you could measure. And he said, here's some rough translation. that in all conceivable situations, it has a practically vanishing value. So he was basically saying, good luck, you're not going to be able to measure something so incredibly small. After the talk, I've got to ask Harold if he would translate this differently or not. So how does it actually work? So the idea of LIGO, simplified to the level that a theorist like me can understand it, it's a way more complicated in reality because there's lots of things you have to do to minimize the noise. But the gist of it goes like this. So this is a laser, and this is a 50% mirror. So we'll shine the laser light at the mirror. Half's going to bounce that way, half's going to go this way. This is the 4-kilometer vacuum tube, 4-kilometer arm. The light bounces off here, and the lengths of the arms are set up so they're not exactly the same. So when some light comes here and comes here, they cancel out. They add up to 0. This is a camera, unless a gravitational wave stretches and squeezes the detector by that tiny amount. Then the cancellation is broken, and you get a blinking signal of light at the detector. Now, actually pulling this off and not having other things shake the mirrors too much, like that's what makes LIGO so hard, and why it took thousands of scientists and engineers decades to actually pull it off. But this is the gist for our purpose of what's going on here. So that's how you can make a measurement like this. And just to remind you, when Michelson built the first one of these interferometers like this, it could measure lengths as small as 10 to the minus 8 meters. So from 1887 to 2015, we had to push this down by a ridiculous number of orders of magnitude to get it down to the 10 to the minus 21 that we need, a factor of 10 trillion improvement. And it would be a whole other course on experimental physics of how that's done. And I'm not the right person to teach that. There are a few gravitational wave detectors. These 3 are operating now. Actually, LIGO is taking measurements right now. Virgo, I think they were offline doing some maintenance. I don't know if they're taking measurements now. Virgo's this one in Italy here. Hanford, Washington's this nuclear waste reservation where they built one in the US, and this one's in the swamp in Louisiana. The US Congress had something to do with where these went, but I don't actually know the whole story of why they ended up where they did. There's other detectors planned, and Kygra has a detector in operation at not yet at high enough sensitivity to make measurements, but they're making progress. And maybe Ajith or Prayush are more up to date than I am, but I know that there's a LIGO detector that's in some stage of some process of being planned and built that's going to be here in India. Okay, so these are the detectors that we have for measuring gravitational waves today. The first measurement of gravitational waves happened on September 14th, 2015. This was actually the day before my 1-month wedding anniversary. And I have to say, my wife was very understanding that I suddenly was working a lot, right? Working long hours for a while. This is showing the stretching and squeezing I was telling you about, but this is a filtered version of the detector's observation. So there's actually noise in here as well as signal. And then this is showing time. This is the stretching and squeezing. And then this is the frequency. So this gives you the idea that the frequency goes up. And I mean, it's just playing it over and over. But the idea of this animation is to give you an idea. This whole thing, the part that LIGO saw, was just a fraction of a second. Okay. Now, since that first observation, LIGO has seen a lot of black holes. Here's a movie that one of my undergraduate students, former undergrads at Cal State Fullerton, where I'm from, made. Each one of these is a numerical relativity calculation. These surfaces are the horizons of the black holes, the apparent horizons. I don't know if you talked about horizons in the course last week, but they're just the surfaces you don't want to fall inside of for our purposes now. That's good enough. And you can sort of see from this animation, there's lots of different kinds of black holes. These are just some of the black holes LIGO's seen. Some are mostly equal mass. Some of them, one black hole is much smaller than the other. Some are kind of the same size. They're spinning, they're shaped differently, they're spinning differently. There's a lot of different kinds of black holes out there. So far, LIGO has seen a lot of things. The horizontal axis here is time, and the vertical axis are the masses of binary black holes or neutron stars or whatever that LIGO's seen. So here's that first one right here I was telling you about. 2 black holes about 30 times the mass of the sun merged and left behind this black hole that's maybe around, in the 60s solar masses. And so the way you interpret this is each pair of dots are the two things that merged, and then they generate a new, bigger black hole. Okay, LIGO's also seen some neutron stars. Here's the first merging neutron stars that famously were observed by just about all the telescopes everywhere. And they've seen some weird stuff. Like here's something that's a little heavy for a neutron star, but a little light for a black hole. And it merged into a bigger black hole. You know, so this is some of the scientific payoff of gravitational waves so far. There's this whole population up here of black holes, tens of 30-ish solar masses that we didn't even know were there before LIGO. Now, the last thing I want to say about LIGO is, so LIGO alternates between measurements and then shutting it down and upgrading it to get better. And so does Virgo and the other detectors. So the first time they ran, they saw 3 gravitational waves and then shut it down to get better. They could have just kept running, but it's way more efficient to shut it down and make it better, because then you'll see way more things when the detector gets more sensitive. And then this is the third observation run where they saw way more. So this is just the number of loud mergers of black holes or neutron stars detected by days that the detector was running. And then right now we're somewhere at the start of the 4th observation run, and this is what we would guess things are going to be. So we're going to be seeing more and more things. So what does numerical relativity have to do with this? Well, because of that tiny number, that 10 to the minus 18 meters, we need numerical relativity to interpret and to help us find the gravitational wave signals. Numerical relativity, like you saw in last week's lectures, it can tell you something about the black hole horizons. It'll tell you about the dynamics, what the horizons of the black holes are doing. In that movie that I showed you at the beginning, that showed the curvature of space around the black holes as they orbit, it tells you that. It tells you all the stuff you want to know about what general relativity says is happening down where things get interesting and complicated, near the black hole horizons. It also predicts a gravitational waveform. This red curve is a stretching and squeezing of a numerical relativity waveform that is consistent with the observation. Now, it's not necessarily the actual thing, but this is a wave whose black holes had masses that were in spins consistent with the observation. And then this thick curve here is thick because there's error from the detector's noise, but this is a reconstruction using approximate gravitational waves that were tested and calibrated to these numerical relativity calculations. So every single thing on this plot, which came from the paper announcing the first detection of gravitational waves, it all depends on numerical relativity. And the bottom line is you need numerical relativity to find weak gravitational wave signals, and even for the strong ones, to interpret them. You have to compare the observations to what general relativity predicts. And that's where numerical relativity comes in. Okay. So before I go on, does anybody have any questions so far about gravitational waves? Yeah. This one. This one.
Some of them are bright.
Yeah. Some of them are bright. So the color is showing the scalar curvatures of the horizons, and the brighter colors are showing more deformation. So the deformation can come from their tidal interactions, and it also can indicate the spins. So some of these are spinning differently, and that also affects it. But it's basically an indication of the shape. Great question. Other questions?
Is it the extrinsic curvature?
No, good question. It's actually the intrinsic two-dimensional scalar curvature of the two-dimensional horizon that I'm showing here. The extrinsic curvature is the curvature of space as embedded in space-time, say, but it's the intrinsic curvature. Other questions? Okay. So that's the picture that's sort of where we are today. Now, to understand why we need next generation numerical relativity, I have to say something about next generation gravitational wave detectors. There's a lot of plans for different detectors. I'll mention some of them. I'm biased. I'm gonna talk about one of them just because I'm as an example. I'm more familiar with it. So we'll start out talking about that, but I'll mention some of the other plans too. So gravitational waves are this brand new way to look at the universe. We don't need light to see distant things anymore. Some distant things we can see with gravitational waves. But today's detectors are only just sensitive enough to see them. So here's an example of some of those plots I was showing you before. In 2015, we could draw time versus frequency and see the gravitational waves here rising above the noise in the two LIGO detectors. Now, if you want to make an analogy, if you think about regular astronomy, Galileo, when he first had a telescope, there were these huge discoveries that he made right away. He saw phases of Venus that gave away that Earth is going around the sun long before we were sensitive enough to measure the parallax effect from Earth going around the sun, making slight changes in the star's motion. And he saw craters on the moons of Jupiter, all stuff like that. But that was just something that you could buy a cheap pair of binoculars and have better power than that first telescope. Today's telescopes are so much more powerful. We would like, so yeah, here's some drawings from Galileo, the phases of Venus that he saw with his telescope, and here's an example of that. Now I'm mentioning this as an analogy because we want to go from this to this, the James Webb Space Telescope, but with gravitational waves. Right now we have the first detectors that can measure gravitational waves at all. And without spending centuries, like happened in the telescope case, we would like to go from just barely being able to see gravitational waves to being able to see the waves we can see today super loud and to see gravitational waves from all across the universe. We're going to need newer detectors to be able to do that. The current detectors aren't sensitive enough, and in principle the facilities limit how sensitive they could even be in principle. And if we want to see gravitational waves across the entire universe and see the loud signals with high precision instead of just barely being able to see them, we'll need new detectors. So this is just one idea for a new detector that would be built in the United States, Cosmic Explorer. And the idea here is it works just like LIGO, but bigger. So the idea is instead of the arms being 4 kilometers long, it's not real. This is just one of the artists at Cal State Fullerton made a rendering of what it might look like. But the arms are 40 kilometers long instead of 4 kilometers long. So just scale up the arms by a factor of 10 or maybe a factor of 5. And then that can help you. That can help you get more sensitivity. Now, there's a bunch of universities getting involved in this. And there's a few other ideas for missions that are coming up or detectors that are coming up that I'll talk more about later. But I'll stay with Cosmic Explorer as an example because it's just a little bit easier to make an analogy with LIGO because it's basically the same idea, just scaled up. Okay, so here's a question I'd like you to think about for a bit, and then we'll have another vote. Would anyone like more time to think before we vote? That's always okay. If not, please prepare your votes. Don't hold them up yet. I don't want you to bias what anyone else might be thinking. And now go ahead and hold up your votes and let's see what you think. Okay. Okay. Okay, go ahead and put your votes down. There was a majority opinion, but there were some differences of opinion. So talk to someone you haven't talked to yet today, introduce yourselves, and convince them real fast, just 30 to 60 seconds why you're right. Then we'll vote again. And make sure if you both agree, you're not both wrong. All right. I know time is short. We'll have to move on, but let's come back together and see if the class came to a consensus here. So prepare your votes one more time, please, and hold them up. Okay, put your votes down. What is the correct answer to this question? Just call it out. It's C. Exactly so. Exactly so. So this is one of the big advantages of new detectors. The same fractional stretching and squeezing, just make it bigger, and now the signal will be 10 times bigger. Whereas, if you build it right, you could imagine the noise is going to be rough. The signal to noise ratio goes up, even if the noise was the same, just because the signal is 10 times bigger now. All right, so this is giving you the idea that you can see the same source, but louder in a new detector. Now here's a follow-up question. Would anyone like more time to think before we vote? Okay, if not, prepare your votes. You can hold up all 4 colors, by the way, if you want to just say, I don't know, or you can take a guess if you're not sure. And now hold up your votes and let's take a look and see where the class is at. Okay. Put your votes down. There was a real rainbow of opinion here. So we're going to do the same thing. Convince each other in about a minute or less why you're right. And make sure if you both agree, you're agreeing for the right reason. And then we'll vote again in about a minute or a bit less. Okay, I can tell there's a lot of really good discussions happening, but we're going to have to come back together. Let's see if the class comes to a consensus. Prepare your votes one more time and hold up your votes. Okay, great. Thank you very much. But you can put your votes down. There was a very dramatic shift towards the correct answer, but it wasn't quite unanimous. So I'll just say a little something about it. So the key here is that LIGO detectors, they're different than telescopes. They're not measuring power, they're measuring amplitude. Now, for all radiation, how does the amplitude depend on distance? If the distance to the source is R, for all radiation, how does it scale, the amplitude scale with R? It's 1 over R. So if the amplitude goes down by a factor of 10, that source is 10 times farther away. And the correct answer was, in fact, B here. So this is the second big advantage of new detectors. By being able to, they don't just see the current things we're seeing louder, they can see things from much farther away. Let me show you a picture of that. This is a picture showing this is a simulated distribution of the black holes, the white dots on the right, and neutron stars on the left throughout the universe. Earth is at the middle because, humans are making it, so we put Earth at the middle. And then this is showing redshift, which is how far away things are from us. Now, this was that first discovery of merging black holes. It was loud even in our early detectors because it was unusually close to Earth. And this was that first binary neutron star discovery, also very dramatic because it was also very close to Earth. It was very serendipitous that the first detections that we got were like this. I always thought, a lot of people always thought, the first things that gravitational wave detectors would see would be something farther away where it could just barely make it out. And there would have been all these arguments about, did we really see anything? But fortunately, we saw these really loud signals first, so there wasn't ambiguity. Now, these lines here, these circles, are showing how far into the universe you can see before the signals are too weak to go below the noise. This curve here is how far LIGO could see in its third observing run. I guess we got to update it now. This is a little better now that they're in their fourth observing run. This curve here is a planned upgrade to LIGO that will actually push how far it can see black holes much farther out into the universe, and it should see a lot more of them. The same curve over here shows it should see more neutron stars, but not yet getting to see most of them. Now, the best you can imagine doing in the current facilities with the current technology is this blue curve. You could also imagine trying to make the mirrors cryogenically cold. There's this idea called Voyager that can do even better. But if you want to extend our range to see all the binary black holes that we think there are in the universe, this purple curve here is how far Cosmic Explorer could see. And similarly, Cosmic Explorer could see just about all of the neutron star mergers in the universe. So by pushing just by a 10 times improvement in sensitivity, you can push the range that the detectors can see much farther out. So the close things are 10 times louder, and we can see things farther away. Now that will allow us to do some science that we couldn't do with the current detectors. It will let us learn what kinds of black holes and neutron stars have been around throughout the different ages of the universe's history. When you start getting to big redshifts, this is getting, to cosmological distances where you're starting to go back and see waves from earlier in the universe's history. And that can tell you something about how stars form and how they've formed throughout the history of the universe. This will also tell you something by seeing the loud neutron star mergers with even more accuracy than you can get today with unprecedented detail. How does neutron star matter actually work when two neutron stars crash into each other? But it's not just the black holes and neutron stars. There could be surprises. Every time we've made great leaps in sensitivity or opened up a new frequency band in an electromagnetic telescope, there's been surprises. And it's possible that these new detectors, or it's possible the current detectors, if we improve them, run them long enough, we don't know. There's always a chance that we could learn something brand new. Maybe there's some small differences from general relativity encoded in the waves that would be a clue to the correct theory of gravity if it's not general relativity. But maybe those deviations are so small, you need these new detectors to be able to see them. So that's just one example. So the payoff that we know we're going to get is we're going to be able to look at black holes and neutron stars throughout the history of the universe, learn about how the densest matter in the universe works. We might learn something new about fundamental physics by comparing with unprecedented precision these loud waves to the predictions of relativity. And who knows, there's all sorts of things that could generate gravitational waves. This is a picture of some cosmic strings. We don't know. Maybe you'll see something like that, maybe not. Now, I promised to tell you about the other detector ideas. One of them is the Einstein telescope, which will be built in Europe. They're in a very good situation from my point of view because there are a couple of countries that, I mean, Harold could tell me if I'm maybe over exaggerating or interpreting this, but it seems like a couple of countries are giving competing bids to build Einstein telescope. And if you've got two people that want it that are bidding, that's a good place to be if you want chances to actually have it funded and get it built. This was a tremendous accomplishment that took a lot of people working very hard for a long time to get this onto the, get this moving through the process in Europe to actually make it real. This is different from the Cosmic Explorer idea. It's shaped like a triangle. So you can think of this as having three detectors all in the same place, but at different orientations. different orientations actually help you because gravitational waves like light have polarization, and the orientations can pick up different polarization. It's also going to be underground. There's not enough overland ground like there is in the United States to want to build one of these things above ground, probably. And then LISA is an idea to put a triangle in space. And this is something that's been talked about for a while, but now it's on the European Space Agency's map. It's scheduled to be launched in the late 2030s, last I checked. And the idea here is you can make the arms way, way longer than you can on Earth, but also the thing that stops you from seeing lower frequency gravitational waves like supermassive black holes on Earth is earthquakes. The Earth is shaking all the time. And if you put it in space, that's not a problem. All three of these detectors will see gravitational waves, the ones we see today, or maybe in a new frequency band. Some of what they'll see will be really, really loud, much higher signal to noise than anything we've seen so far. But to build these detectors, there's all kinds of challenges. I'll just show you one for the detectors on Earth like Cosmic Explorer. It turns out you can't make an arm too long or it will stretch and squeeze before light has time to go down and back. And so if you want to see high frequency gravitational waves like LIGO, there's sort of an upper limit of around 40 kilometers before the arm is too long. But there's another issue, which is if you start building 40-kilometer detectors, the Earth actually isn't flat. Lasers don't follow the curvature of the Earth. So here's a little cartoon, not to scale. If you have a 40-kilometer arm and the Earth was a perfect sphere with its average radius, then the part in the middle would have to be 30 meters up. And from an engineering point of view, that sounds really expensive. Like you don't want to build like a giant bridge or something like that. So what you want to actually find is something like what I've shown here, a place on Earth where it's actually flat. I mean, Earth is really a sphere, of course, but we want to find a little piece of it that's as close to flat as we can to make it as easy to build so you don't have to do a lot of earth moving or do something ridiculous like build a big bridge or something like that. So that's just one example. Finding a place to build something so big is hard. There's also technical challenges I don't have time to go into about actually, there's some research to be done on how to make the vacuum systems and the optics and things like that actually scale up. But the gist of the idea is do LIGO, but make LIGO but bigger. Now, there's another complication, which is the pendulums aren't going to hang straight down. They're going to hang towards the center of the Earth. So there's just all kinds of things you have to worry about. Now, that's what I wanted to say about the detectors. Where does numerical relativity come in for the next generation of gravitational wave detectors? Well, let me show you something. So this was a plot I showed you earlier in movie form. This is detector data that's filtered to reveal from the two detectors, Hanford in orange and Livingston in blue, the gravitational waves. And here they're overlapping each other. This is the signal, but then over here where they're different, that's just noise. Now, what I'm showing you here in the bigger plot, the purple curve is a simulated LIGO noise after the coming upgrade A+. After this A+ upgrade, which hasn't, it's planned, but that's in the future. Then there is this wave in there, but also there's a lot of noise. This doesn't look like the real gravitational wave signal. This is just raw, unfiltered, simulated data. But if you had Cosmic Explorer or LISA or Einstein Telescope, then you could get something more like this. This is just unfiltered data. You just look at the raw stretching and squeezing data. This is in units of that number, 10 to the minus 21, and you just see the wave. What that means is the experimental errors here are way, way smaller. And that means your numerical simulations have a lot less wiggle room. In order to avoid biasing the interpretation of the observations, you need to have numerical errors that are smaller than the experimental errors. And when the experimental errors go down, these errors have to get, your numerical errors have to get a lot better too. Uh-oh, somebody said the screen is dark. I don't know if that fixed it or not. Everyone here can see it. I don't know what's going on Zoom. Maybe I better just go on. So, next generation numerical relativity. It turns out, and I'll give you a feel for why this might be in a minute, some recent studies suggest they're the first cut of how good our numerical relativity waves going to have to be. They're going to have to be much better than what we have today. Today's best waves are something like 10 times not accurate enough for these future detectors. Now, an even bigger challenge for future numerical relativity is if you've got neutron stars or matter, like you learned about last week, just how much more complicated that is. But even the binary black holes are a stepping stone. If you want to have a black hole and a neutron star merge in your simulation, the black holes have to work first, and the neutron stars have to work before you can put them together. And also, there are some cases of merging black holes where the spins are really high or the masses are really unequal, where new codes, next generation numerical relativity, could give you performance that would let you do these simulations that you couldn't do otherwise. So here are these three detectors that I talked about. Those are the motivation for why we want to do this. And then the idea is we want to be able to model something like this yellow curve with sufficient accuracy. Okay. Now, one big challenge is that getting more accuracy is hard, and I want to give you a feel for why. So I'm going to talk about the signal to noise ratio, which I'll call rho. This is just the strength of the signal divided by the strength of the noise. How accurate your gravitational wave model needs to be depends on the signal to noise ratio. If the signal to noise ratio goes up, then you have less wiggle room. Okay? So how much less? Well, it's complicated to actually answer that question precisely, but you can get a first cut at it by using these sufficient conditions. They're sufficient in the sense that the question is, okay, if there are some conditions that if they're true, two waveforms are indistinguishable. So why do you care about that? Well, if you have the true wave and your numerical wave, and you compared them, you would like them to be indistinguishable for a detection at however much signal to noise ratio you've got. If they're distinguishable, then that means your model is not accurate enough. So what is that condition? Well, it's a little complicated. So let me introduce a bit of math real quick here. So if you have two gravitational wave signals, and here I'm writing them as functions of frequency and not time, H1 and H2, and you do an inner product of them, but it's weighted by the noise. So in the denominator, you put the noise, S. So this is like a dot product of two waves. You can think of it like that. And this dot product is just your ordinary inner product of two functions over all the frequencies, but it's weighted by the noise. So if the noise is bigger, this denominator gets bigger and makes those contributions smaller. So this is a noise-weighted dot product. And the idea here is there's something called a mismatch. If two waves are exactly the same, then this dot product would be 1. So you take 1 minus this dot product, suitably normalized, so that this thing would be 1 if the two waves are exactly the same, then the mismatch would be 0. So if this dot product is 1, these dot products are 1, so because you've normalized this to make this a unit vector, then this thing would be 0. The mismatch not being 0 means the two waves are not the same. So you can just think of this as the waves are vectors, and you're just dotting them together. How close are they? Well, it turns out that the mismatch, the waves are indistinguishable if the mismatch is less than something that scales as 1 over the signal to noise ratio squared. Now that's a sufficient condition. It's not necessarily true that the waves have to be this good, but this is something that's easy to evaluate to give you a feel for how much better do they have to be. It goes as this 1 over the signal to noise ratio squared. And that brings me to one of the next, I don't know, this might be the last one for today, another vote I'd like you to think about. Oh, and I guess where this says the two waves, that's a typo. This should just say two detectors measure the same wave passing through both detectors. Oh, maybe it's actually not a typo. Okay, would anyone like more time to think before we vote? Can you show that question from the switch again? Yeah, so the question, oh, the definition of mismatch, sure. I'll just show that. So it's this thing right in the middle is what you're looking for. All right, we'll take a little more time to think about it, then we'll go back to the thing and vote. Let's see what happens. Go ahead and prepare your votes. And hold up your votes. Okay. Okay. Go ahead and put your votes down. There was a majority opinion, but there was still some disagreement. So one more time, in about half a minute, convince each other why you're right, and we'll vote one more time.
Mismatch expression you know.
Yeah.
So usually when we talk about mismatch between two models, we compare like an analytical model with the NR model, right? So in this case, when we talk about the accuracy of the numerical models itself, which are the two models we'll be comparing?
Yeah, so it might be like numerical waveforms at different resolutions.
Okay, thanks. Yeah.
And that'll give you an idea of the accuracy. I should have clarified that. I'll say something about that after this question. Okay, let's come back together and have one more vote and see what happens. Prepare your votes one more time and hold up your votes. Put your votes down. What is the answer? It's A. Yeah, exactly right. Because of the scaling of 1 over the signal to noise ratio squared. Now, there was a good question that someone in the front row just asked me here, which is, what are the two waveforms we're talking about? So the idea here is, I should have clarified this. When we're taking a mismatch, when you're measuring the accuracy of a theoretical wave, you're not taking a mismatch of like the data and the model wave like you often would do. The mismatch you're talking about is maybe you have your wave at two different resolutions, and to get an estimate of the error of the wave, you would take the mismatch of the lower resolution model with the higher resolution model. So I should have clarified that. And so the idea here is, if your two waves that differ by the numerical error differ enough that they're distinguishable in this sense, then that could cause problems for interpreting the gravitational waves. And it turns out, because it scales with the signal to noise ratio squared, that if a mismatch of some number is fine today, it's got to be 1% of that when your detector sensitivity goes up by a factor of 10. And let me show you what a problem that is. This is a plot from the Simulating Extreme Spacetimes Collaboration's catalog of gravitational waves. Just look at this top panel here. This is a histogram showing how many of our simulations, when you take the two best resolutions we have and compute the mismatch, how many of them have different levels of mismatch. So the idea is, if the error in the waves was 0, then the mismatch would be 0. So more error is this way, less error is this way. Now, for a signal like the first gravitational wave detection, where the signal to noise ratio was 24, then when the accuracy of our waves found by computing the mismatch of the highest resolution and the second highest resolution would have to be to the left of this green line to be good enough for those waves to not be distinguishable when you're measuring that observation. So everything to the left here in our catalog is fine. So some of the simulations aren't so good. Most of them, they're not distinguishable in this sense when you're using them to model GW 150914. But if you saw a signal to noise ratio 1000 signal, like the new detectors will measure, the simulations to the left of this red line are the ones that are good enough. Most of them are not. This is putting a few more numbers on this claim that we've got to get an order of magnitude better. Okay, any questions? Yes.
So in the green curve case,
Yes.
compared to what we were changing compared to the second generation detectors is the noise PST. So that's the only difference, right? In the mismatch calculation.
I'm sorry, can you just say that one more time?
Like in the green curve itself. So we
Yes.
are looking into a GW 150914 like signal in the 3G detectors, right?
Oh, you're saying which detectors? Is
Yeah,
that the
so
question?
for the green curve,
Yeah.
that is the 2G detector itself.
Is it for LIGO? Or
Oh, so like what noise was used? That's the question. Okay, I should have clarified that too. Thank you for asking that. Great question. So when we compare, okay, I'll try to remember that. I'll come to that question next. So to compare, so when you compare theoretical waveforms like this, usually what we do is we use a flat noise curve. So it's not for any real detector, because we wanted to say how accurate are the waves intrinsically before you apply them to a specific detector. So in this case, the noise that we used in the inner product was just one. And so it's not weighted to favor any frequencies over any others. You could redo an analysis like this where you put in LIGO or Cosmic Explorer, but here I'm just looking at the signal to noise ratio, but assuming a detector that doesn't have any frequency dependence.
But how do you define the signal to noise?
Yeah, so it's not that there's no noise, it's that the noise is assumed to be uniform in frequency. Just so that the problem is, this is a bit of a detail I wasn't meaning to get into, but if you use the LIGO noise curve, that will favor some frequencies over others. And that means that some numerical errors would be suppressed, the ones at the frequencies that you don't see as well. And this particular plot that I chose to show you was in a theory paper where we wanted to emphasize the accuracy of the waves independent from a specific detector. And this is a choice that's commonly done in that case, to say, we're going to look at what this would be for a detector that's equally sensitive at all frequencies. In real life, that's not true, but that's just how we made this figure. You could have made it the other way.
So in the mismatch inequality, the m less than
Yes.
4 by rho square. So when we say we change the detector sensitivity, that just means that we change the SNR to some factors
Yes,
of 10.
to some other number. So picture a flat noise curve. In LIGO, the noise is high at low frequencies and high frequencies and lower in the middle. So it's sort of like this shape. But this plot is assuming a noise curve like this. It's not that there's no noise, but when you turn up the signal to noise, you're just imagining lowering all the noise together. Now, there was a question about chirp mass in the chat. Let me see if I can see that. Why does higher chirp mass binaries cause more error? I don't know. I'm not showing anything about chirp mass here. So what was that? Oh, yeah, sorry. This curly M is mismatched. There's no chirp mass. This is just I don't know if that was it. I don't know. I'm sorry. I don't understand the question. So I think maybe if you message me afterwards. What is the y-axis? The y-axis is the fraction of simulations in our catalog with this level of mismatch or this level of accuracy. So 6% of all the simulations in our catalog fall into this bin when we did the mismatch calculation. So basically more simulations is the one. You want more simulations to the left of the line. Yeah, so like you want more tall bars to the left of the line, because then the mismatch is small enough that for that signal to noise, the waves are indistinguishable. And then you won't have to worry about differences in the two waves at two different resolutions, say, affecting your interpretation. Yeah.
So if you think about third-generation detectors, for example, you did simulations to the left of
Yeah.
right? So the current simulations are not going to be used that time. So is there a way to like improve these existing simulations rather than like regenerating?
Oh, that's a great question. So instead of making new simulations, could you somehow improve the current ones? I think that's really hard, because the simulations, like Harold said in his lecture, basically the resolution comes from your choice of n that truncates these series expansions. And once you make that choice, all the higher terms are gone and you can't get them back. It's sort of what I think what you're asking is analogous to if there's this blurry photo that shows the bad guy in a movie and the cop says, can you enhance it? And then they push the enhance button. But that doesn't really work because the data isn't really there. So maybe with some kind of AI thing, you could create something that's not really the real signal, but is close enough, just like these AI image generators can do it. But I don't know. I think it's really hard. It's a great question, but I think that's really hard. Yeah. I'm sorry, can you say that again?
The second graph, you have used psi 4.
Yeah.
So is it the conformal factor or is it something?
Oh, thanks for asking about that. No, the reason I said just look at the top plot, because this is the strain H, was I was going to gloss over this. So there's two different ways numerical relativity codes calculate the gravitational waves. One way gives you the strain, which is the top plot. Psi 4 is one of the Newman-Penrose scalars. It's a component of the Weyl curvature tensor. And basically, it's the second time derivative of H. And so we just checked with these two different measures of the gravitational wave. But no, it's not a conformal factor like we used last week. It's a totally separate thing. Yeah.
Can you just go to the slide where noise rate is normalized?
Yes, I can do that. Maybe. I thought I could do that. Here? Good question. What are H1 and H2? H1 and H2 are two waveforms you want to compare. You could use this formula very generally. H1 might be the measured signal with noise, and H2 might be a model waveform. Or they might both be model waveforms. The way I'm using them is I'm saying, suppose we want to measure the accuracy of our waveforms. And let's suppose we do the same calculation at two different accuracies so that we can get an error estimate. Then H1 would be the lower resolution and H2 would be the higher resolution. But it doesn't have to do with the detectors in this case. Now, I said detector noise would be what's weighting it here, but in the plot I was just showing, we had a detector where the noise was the same as all frequencies, so it wouldn't really change this. But H1 and H2 here are like the less accurate and the more accurate, and when you compare them, that gives you an error estimate. Yes?
By generating a more accurate waveform, so you are also compromising on the compute time. And will you take this into account? Should you worry about it?
That's a great question. If you want more accuracy, isn't that going to be more computationally expensive, I think is the question. And the answer is yes, and that's why we need new numerical relativity codes, because they'll be designed to scale to more processors to help overcome the greater computational cost. Yeah.
Once the template is ready, then you don't require it further. So while doing the analysis, for example.
Yeah, so numerical relativity, I think what you're getting at is a good point. Numerical relativity calculations are so slow that we can't create the millions of waves that we need. So I briefly alluded to these approximate templates. They're tuned to numerical relativity. They're tested against it. So in that sense, they still rely on it. But you're right, when you actually interpret a specific observation doing what in the lingo is parameter estimation, you're not using numerical relativity usually, although there are some approaches that directly use the numerical waves where you don't need so many. Does that answer what you're asking? Great. And I think there was a question on Zoom, but it disappeared. So let me see if I can get that. Can combining data from multiple detectors improve the signal to noise? Yes, it definitely can. And that will also improve the accuracy. So yes, if you have more detectors, then I'm not accounting for that in this argument, but yeah, that will give you more accuracy, and the more accuracy you have, the better your numerical relativity waves must be. Okay, one more question, then maybe I'll go on.
So you lose the higher order terms, right?
When you truncate the series, yes.
So what it creates inherent bias, and if you're looking for more different mergers, would it kind of mess up our
Yeah, so if I understand the question right, the question is, if you truncate the series expansion and these spectral expansions, then doesn't that mess up the observation? And the answer is, it depends. It depends on if you kept enough terms that the difference between your wave and the true wave is sufficiently small that the true wave and your truncated wave are indistinguishable. So the point of this mismatch calculation is to give you a feel for, are these two waves a lower resolution wave and a higher resolution wave, which you use to stand in for the wave you calculated, and the true one, which you don't know, that's infinitely accurate. And the idea is, if they don't differ by enough, it's fine. But if they differ by too much, then yes, exactly what you're saying. It would contaminate, it would bias the interpretation. And so we need more accuracy precisely to avoid that happening. But if you truncate the series high enough, then that won't be a problem. The question is, how high is high enough? And the way we've been truncating those series expansions in our codes today leaves you with the answer that for today's detectors, it's okay. We're truncating the series, and it's not just one series because it's not just a 1D problem, but all the series expansions we're doing, they're truncated at high enough order that for most of our simulations, the difference between, or our estimate of the difference between that and reality, or that and infinite accuracy, is so small, the waves aren't distinguishable at this signal to noise ratio, but they would be distinguishable for the future detectors. So we need better accuracy for the future detectors. Does that answer what you're asking? Okay, I think I'd be happy to answer more questions at the end, but I want to go ahead and use that question as a launching off point for finishing up the talk today in the last 20 minutes. So today's codes only truncate the series expansions well enough for today's detectors, but not for the future detectors in general. Why is that? Well, it's how long are you willing to wait? Today's codes are only so fast, and we usually set the truncation to what we can live with. There's some universal rule, I don't know who I heard this from, maybe it was Harold, in numerical calculations, that the longest you're willing to wait is something like a few months. So whatever you can get for a few months worth of calculation. Now, there's two different paths you can take to try to do better. You can take today's codes and try to scale them up, or you can use novel techniques to try to get the codes to scale up to make use of more computational power so that for the same 3 months, you can have more terms that you keep in your series expansion. Now, there's a bunch of codes that are taking the second tack. Spectre is one of them, and that's the one we're going to play around with in the tutorials. But there's a whole bunch of others. And these codes are using some different combinations of techniques, like NMesh also is using discontinuous Galerkin. Some of these codes, I think Athena++ is also using task-based parallelism. So some of these techniques I'm going to talk about are in common. But I wanted to give you I wanted to acknowledge that while I'm going to spend the class talking about one code, the code that I and my collaborators are working on, because I know it and can show it to you, there's actually a big effort from a lot of groups to build a new generation of codes. And there's some references here if you wanted to go look at them. Yes?
This may be relevant, but why does it seem like hydro and beyond GR are mutually exclusive?
Why does it seem like hydro and beyond GR are mutually exclusive? I think that's a coincidence of the ones I highlighted. I don't think there's any reason why you couldn't do both. In Spectre, I don't think I would say beyond GR when this table was written because we hadn't published it, but certainly people are working on adding that to Spectre. It's just, it wasn't ready at the time. So I never noticed that before. Thanks for asking it, but I think it's a coincidence. Yes. Oh, yes. So for formulation, that's right. So there's different ways to write Einstein's equations. I think you looked at the BSSN formulation last week. So GH is the generalized harmonic formulation. And I think they, for whatever reason, I would usually just call it generalized harmonic. They called it generalized harmonic gauge. But yes, that's what it is. But it's not really the gauge. It's the formulation of the equations. Yeah. Thanks for asking about that. These are great questions. Okay. So I'm going to finish up in the last 20 minutes by saying a little bit about Spectre and then a little bit about task-based parallelism. Here's Spectre's website. Most of you, or if not all of you, went there to follow some instructions to set up Visual Studio Code and Docker and Spectre. And that's the environment we're going to use for the tutorial this afternoon. We'll work in groups, so it's okay if you didn't do that. You'll just want to get in a group where someone has a computer with that environment set up. If any of you have trouble getting it set up, you can always come see me sometime this week, and I'm happy to help you out. So what's the deal with Spectre? Spectre, unlike Spec, our current code, the new code, Spectre, is open source, so anybody can get it. You don't have to be a member of our collaboration to use it. It's on GitHub. And it uses discontinuous Galerkin, except where there are shocks in the matter, sharp features. It falls back to finite differencing to do all the fancy shock capturing stuff that you learned about last week. I'm not going to focus on that much. I think the vacuum part, where the solution is smooth, the DG part, is plenty for this week, so I'm going to emphasize that. So let me give you a first feel for what is DG all about. Well, discontinuous Galerkin and the spectral approach that Harold's talking about aren't really completely separate things. Now, mathematically, you might do the derivation of how you turn your continuum into a discrete set of grid points for your simulation. You might do that math differently, but basically it's the same idea. In both cases, you expand everything you care about in your calculations in terms of some basis functions. Now, I'm going to not do the n-1 thing, so sorry. I mean, Harold had a good point, but I'm just going to say we're truncating at some finite number. And then use the coefficients are what you solve for, and then these are basis functions you know, like the e to the I kx that you looked at this morning in Fourier series, or like Chebyshev polynomials or Legendre polynomials or whatever. In practice, what makes these methods different is that DG tends to have more elements that are smaller, and the older or the more traditional spectral methods will tend to have fewer elements that are bigger. But they both have some things in common. As you turn up the number of, both of them divide up your domain you want to simulate into a bunch of little elements or cells. This is something they have in common with finite element methods too. They divide up the space into a bunch of cells. There's just more cells that are smaller. So you tend to have fewer terms in the series expansion in DG, but more cells. But you tend to have fewer cells, but with a bigger N in the spectral code, at least in practice. But in principle, there's nothing necessarily so different. And as you turn up the number of terms you keep, if you do what Harold said you had to do, and you choose the correct basis functions for your problem, suitable basis functions, and you do the problem correctly, then the error will decrease exponentially with the increasing number of grid points in each element. You can also make the error go down, not exponentially, by just carving the elements into smaller elements. And you can take derivatives exactly like Harold showed you, because you know what these basis functions are, you can differentiate them. So those are some advantages of this kind of approach. The other way you can do this is, in the way almost all numerical relativity codes work, is finite differencing. Where there, you're not dividing the space up into elements, you just lay down grid points. And here I've laid them out in a regular way, but you can do fancy things like put a denser grid where you need it. But then if you want to take derivatives, you could go like, point on the right minus point on the left divided by the distance between them, or a fancier version that uses even more neighboring grid points. So there are trade-offs. This thing is the best, most robust approach when there's shocks, like when there's matter. These require smooth solutions, just like you heard in the previous lecture. But they're really, really good when the solution is smooth. Now, there's some downsides in terms of how well these codes can scale. So we'll come back to this movie in a second. A big problem with finite difference codes, if you want to run on 100,000 processors instead of just 1,000 processors or 100 processors, is that they need, when you take derivatives, you don't really just go like point on the right minus point on the left. That's not terribly accurate. You want to do a higher order derivative, which means you need more points. And that means if you distributed these points on different cores, they're going to have to communicate with each other more. And eventually, those communication costs, sending values from this point over the network to this point on a different node on the cluster, the supercomputer you're using, that becomes prohibitive. And so that's something that's challenging, trying to scale these methods up. A nice feature here is in these methods, each element or each cell only needs to talk to its nearest neighbors. It doesn't, because you don't take these wide stencils to do derivatives. Now, let me show you this movie. This is something that Niels Deppe, who's one of the lead developers on this Spectre code, made. I'll show you this movie again. This is just a test of some fluid, and it forms shocks. And you might see these little tiny grid lines. Those are places where the code has fallen back to doing finite differencing to handle the sharp features. But everywhere where there are no sharp features, it continues to use this method because this will give you this much greater accuracy at much less cost because of the exponential convergence. Now, in order, this is just one of the two big techniques I want to emphasize about Spectre, discontinuous Galerkin. I'll be saying a lot more about it in the other lectures this week. I'll go to the board and show you the math of how you actually do it. For today, I just wanted to give you a feel for what it's going to be like, and to tell you that it's not totally different from the spectral approach that you're learning in Harold's class. Now, the other thing is parallelism. Our old code spec and most numerical relativity codes use a data-based parallelism approach, where I'll say more about it later, but basically you run one copy of the code per core and some if statements split up the work to work on, this grid point or this cell or that cell. Task-based parallelism is a different approach, where you've just got a bunch of bits of work that need to be done, and there's some scheduler, and if a core is free to do some work, the scheduler will say, hey, don't be lazy, here's some work you can do. It's just a different way of doing parallelism. It's much more complicated to code. That's why we're going to take a whole week to write a simple toy example using task-based parallelism, but it has the potential to scale much better. One reason is task-based parallelism is less synchronous. So let me give you an analogy. So the spec way of doing parallelism, data-based parallelism, has a lot of synchronization points. So this is where the different cores have to pause and wait for each other to catch up. So picture being on a Zoom call, like on a Zoom call, and someone's trying to talk, but they're muted. I did that teaching a class once. I felt really bad. The students took a while getting my attention. It's a pain. Everyone has to wait. This task-based parallelism approach is more like messaging each other, like on Slack or texting each other. So here, if I need data from my nearest neighbor in Spectre in task-based parallelism, you'll just send a message and say, hey, I need some data, and then hang up the phone. And while they're getting back to you, you go off and do some other work that the scheduler gives you. And then eventually you'll get a call back or a text back that says, okay, here's your data. And then the scheduler will have you come back and deal with it. So there's just less, it's more asynchronous. It's more like sending messages and dealing with stuff as it comes in. I'll make this more precise later on. But that's the gist of the two big techniques. So I've told you why we're going to use why we want new numerical relativity codes. We want to get that much higher accuracy that we'll need. And one way to do it is by redesigning the codes so they can run on more processors at a time. So they can achieve more accuracy with less cost. And the two techniques that Spectre uses to do that is the discontinuous Galerkin approach, unless there are shocks when it falls back to the usual finite differencing thing, and task-based parallelism. Those are the two things I'm going to tell you about for the rest of the time this week. Now, in the last 10 minutes, I'm just going to briefly introduce task-based parallelism as a concept, and then we'll spend the whole week in the tutorials actually building something that uses it for real. Okay. So with data-based parallelism, what spec might do is suppose you had a black hole in your domain with something like this, a bunch of concentric spheres. You divide it up, there's a hole in the middle where the singularity is, we remove that. And then the part of the space around the black hole you're simulating is this gray region. We divide it up into a bunch of elements, which in a spectral method might be spherical shells. And then in spec, you just put one cell maybe on each processor. And that's the limit of how many processors you can use. You're dividing the work up among the processors by the data that you're solving. That's why it's called data parallelism. So you're solving for the solution at different parts of the grid, and you just put different parts of the grid on different cores. And then you've got some code that will do things like solve the partial differential equations. Once it's solved it, find where the horizons of the black holes are, compute the gravitational waves being emitted, stuff like that. And in this approach, so here you just put one specific cell on each core, and then you just run the same exact a copy of the same exact code on each core. And there are if statements that say, if processor 0, do it to this data. If processor 1, do it to the data in this cell here. And that's it. It's a simple way of doing parallelism, with the downside that there tends to be more times that it needs to sync up. There tend to be more times when some cores are waiting for others. Now, task-based parallelism is more complicated, but avoids some of those problems. So how does task-based parallelism work? So here's a grid from Spectre. I've labeled each element. So here's element 0, element 1. Each element's called omega. When I go to the board, I'm going to be talking about the kth element, and I'll write omega sub k to talk about the kth element. This grid has 47 elements on it, I think. And the idea is we want to split those elements up among the different processors, the same as in spec, but there's more of them and they're smaller. So the idea is we'll split up the elements onto the different cores, but what I've drawn here is it's not just the element. Each of these little boxes isn't just the same code running on the same data. These are, you can think of these as actors, as little independent units of code. I'm calling it a parallel component here. And then there are a couple of other, but what a parallel component is it's a thing that has some data and has some things it can do. So it has knowledge and it can take actions, and they can talk to other parallel components. So these are like objects in an object-oriented language, but they can be spread out over multiple cores. Now, you might also have some of these objects that can take actions and hold data that aren't like one per element, not a whole array of them, but there's just one of them. So one core might have a component whose only job is to take data and write it on the disk. Another core might, and you might also have something whose only job is to read in the initial data for the simulation, and then it's done. It doesn't do anything else. You might have one that finds apparent horizons in your code to find where the horizons are. You might have one that controls if you have to move the grid as the black holes. I might talk about that if there's time. As the black holes orbit each other, we have to take the grid and make it move around to track that motion. There's something responsible for that. And then you might observe gravitational waves or other things. So this design is a little bit different. Instead of just running the same code on different cores have different codes. Some of it is each element is doing the same things on its data, but then there's also individual components that only exist on some cores. It's not the same code on each core. And then there's also maybe some globals that are available on every processor. That's what I put in pink here. So this cartoon is just to give you the idea that it's not the same thing on each core, except just a different element. Each of these, now what are these things? I want to say a little more about what these parallel components are. Think of them like an independent actor. It has some data that it stores, it knows things, and it can do things. If you're used to object-oriented programming, these are objects, but they're distributed. So this parallel component can send a message to call a member function of a component over here. If you're used to thinking about object-oriented programming, you can think of it that way. If you're not, don't worry. And let me show one of these, just one of these, the kth one of these element parallel components in more detail. It knows things and it can do things. So in Spectre, this is called a data box, but this is just basically a dictionary of data. You have some label, which we call tags. I'll say more about how you make those in C++ later in the tutorials. But basically, there's a name, and each name points to one bit of data stored in memory. And you might have a whole bunch of things stored in memory that this particular object knows about. And it has some tasks that it can do. These tasks might be, take a time step in your simulation. They might be, ask for some data from your neighbor that you need to do boundary conditions with your neighbor. Every single action that you do, we just call these actions in Spectre, but these are the tasks of task-based parallelism. These are the actions that you can take. Elements know how to take some actions related to things like taking time steps or telling people about what kind of resolution they have, where their good points are. There's all kinds of things. This is very generic. And so think of this as like the nouns are the data and the verbs are the actions. Okay. So one action might be to initialize some data or to change it, like to update it as you take time steps. So the idea of task-based parallelism is you'll need to make a bunch of these independent parallel components, these actors, and then give them things to do and data to operate on. There's also a possibility of having some global things that everyone has access to, but without having to send a message and ask for some data. So the key thing is these can talk to each other. So you can send and receive data from element 0 and to element 16 if you needed to. Or maybe more realistically, because these aren't nearest neighbors, so they would never have to talk to each other, the horizon finder, maybe the horizon intersects element 0. And so the horizon finder will need to send data back and forth. They can send messages back and forth, they can send data, and they can call each other's actions. Their actions are functions that you can call, and you can call it even if it's on a different core. Spectre uses a library called Charm++ to take care of the details of that. So from your point of view, when you're writing code for Spectre, it doesn't matter which core these objects are on. The underlying framework takes care of the communication. Okay. Let me just finish by comparing these two ways of doing parallelism. With data parallelism, you run n copies of the code on n cores. That's a different n, possibly, from the n truncating your series expansions. Task-based parallelism, you distribute a bunch of objects on different cores. Then in data parallelism, you run the same exact operations on all the cores, just on subsets of the data. But in task-based parallelism, you can run different computations on different cores, on the same data or on different data. There tend to be fewer synchronization points in task-based parallelism. You're less likely to waste time. How much time is wasted while you're just waiting for the other cores to catch up in database parallelism can be a lot. In spec, more than half the time in some simulations is actually spent where some elements are waiting for the slow ones to catch up, especially in simulations where some elements need to be much higher resolution than others. Now, the key takeaway is how much you can parallelize, how many cores you can make efficient use of is proportional to your data size. So it's limited by how many elements you have. And in spectral methods, you tend to have not very many elements. But in task-based parallelism, you're not limited by the data size. You're limited to how many tasks you have that are independent from each other. So by carving the work up into a bunch of small pieces, you can, this is how task-based parallelism can help you scale to way more processors. So I think I'm about out of time. I'll be happy to answer a couple other questions, and then I realize I'm standing between you and lunch, so I'll stop there. Yes. Sure. Oops. Sorry, it'll take me a second to get.
This parallelism we have is array component set for each course.
Yes.
And so I think now so these array components, can they share information to other courses?
Yes.
And so that means they are not static for each course.
Yeah, so that's right. So in principle, you can actually move a component from one core to another, and the framework like Charm++ or whatever you're using to do the parallelism, in principle, can do that. In practice, Spectre hasn't enabled that yet, but in principle, yes, you can actually move components around. Which processor they're physically on doesn't matter from the code's point of view.
So these cores are like, each program is run by these cores, right? Programs are different.
Yeah, so the actions that in here only care about writing to disk, whereas the actions in here might have to do with taking time steps. And the actions in here have to do with finding horizons, and they're just different on different cores.
And actions are such that these arrays can be used to other cores as well.
Yeah, so this component can call the actions from this component, even though it's on a different core or a different node. And the framework, whatever parallelism framework you use, will take care of getting the messages back and forth on the hardware. usually you would use a framework. It doesn't have to be Charm++, but something where you're not having to handle the messaging yourself.
Can I say that these so since these array elements are being called to other codes as well, so these are somewhat reduces the number of processes that individual processes to capture something for program.
I don't know. I'm not sure I understand, but what I would say is the more little elements you have, the more cores you can make efficient use of, because each element has its own tasks to do that are independent, and some of them need data from their neighbors, but other than that, they're independent. And so the more little elements you have, the more cores you can make use of. If you have too few elements on a core, you might run out of tasks to do, and then you have the same problem as in the data-based approach. Yes. How do you decide on a particular set of elements? I'm sorry, can you say it one more time? Yeah.
This would have required the horizon finder this task.
Yeah. Oh, how do you know which elements need to send data to the other? Yeah. So in principle, you take care of that with messaging, but in Spectre, what actually happens is all the elements currently, because we haven't done something smarter yet, all the elements will send data to the horizon to ask if it needs to be interpolated, and the data that's in the wrong place just gets discarded. So it's currently doing more communication than it needs. But in principle, you could do something smarter and have it use messages to figure out which data needs to be sent. We haven't implemented that in our code yet. Yes.
Division is possible in space or like time as well?
Well, now that's an interesting question. Is the division possible in time as well as in space? Yes. In fact, Spectre uses something I'm probably not going to have time to go into, but there's a chance, called local adaptive time stepping, where different elements can actually take different sized time steps. And then the math can take care of combine it when the neighbors have to communicate, combining the information of the different steps.
Later times will require information from the earlier times.
Yeah. Yes, but there's a way to do that even if the time step sizes are different. And there's a paper by Will Throw who implemented this in Spectre. But adaptive time stepping, local time stepping isn't a brand new idea. It's just not commonly used in numerical relativity. Great question. Okay, well, I think we're a few minutes over, so I'm happy to answer other questions right after the break. But thanks, everybody. I'll stop here, and I'll see you at the tutorial today at 4.